the last bit of scattering we're going to talk about is the two things. We're going to talk about symmetries of the S matrix and also wave packets. But back to the S matrix, where we left off before is what we're trying to show that, and again, S matrix is the interaction picture, evolution operator for scattering, free particle in the infinite past, and a scattered particle in the infinite future. It's the asymptotic states. And what we're trying to do is show that the matrix elements, in terms of the momentum representation, that these matrix elements are given by an inner product between the incoming and outgoing scattered solutions. Well, these are the full scattering solutions to Schrodinger's equation. Now you see, it's nice. It's like it gives you a concrete connection between the time evolution of a scattering problem and the scattered states. So that's kind of what we're doing towards the end here, is we're trying to connect the stationary scattering problem that we've been looking at this whole time to the actual time dependence. Because a true scattering problem, you would have to package it in a wave packet and then see how it evolves in time. But the properties of that evolution are essentially determined by the stationary state scattering solutions. They're what tell you what's going on inside the wave packet as it scatters. But we're going to try to prove this. And last time we left off, we argued that these scattering solutions, the incoming and outgoing ones, they're given by the incoming plane wave, and then plus a Green's function that doesn't invert just the kinetic energy alone, but also the scattering part. So this is the full Hamiltonian, not just the kinetic energy. And we argued that this is an expression for the scattering solution. So this is just a rewritten version of the Lippmann-Schwinger equation solved iteratively, right? This is basically the Born series again, because you can expand, Taylor expand in the potential V, and you'll get the Born series. So like to leading order, you would just get the Born approximation. So that's our beginning. And so now what we want to do is actually calculate this inner product using this formula, and then using what we understand about the properties of the Green's function. So the first thing to do is expand the and it's worthwhile to put a little K label on the energy to just remind you which K the energy is associated with. It's sort of a worthwhile thing to do. And so let's start calculating this inner product. We want to expand this bra first. So this is K prime dotted into psi of K vector plus, and then we have plus K prime dotted into this Green's function. Now we're expanding the K prime piece, so you want to put a K prime there. minus h, and this is plus I epsilon because we have to take the complex conjugate. We're expanding the bra portion, and then this is v dotted into psi k plus. Okay, so that's the first step. And then what we do is we can use the Lippmann-Schwinger equation to expand the forward scattering part. So that would give us k prime dotted into k. That's just the first term in the Lippmann-Schwinger. Then we have, as part of the Lippmann-Schwinger, we would have k prime dotted into 1 over e k vector now, because it's the Lippmann-Schwinger, minus h naught, just the kinetic energy, plus I epsilon, and that's dotted into psi k vector plus. So that's just this first term. That's just taking it and expanding it out, using the Lippmann-Schwinger equation. Remember, it's a kind of recursive equation in that it's an expression for psi plus k in terms of psi plus k. I'm missing a v here. So that's that first part. And then we have the other part, which we're going to sort of leave alone. Okay. So now what we do is we have to think about what states represent eigenstates of the Green's function. So for instance, we know that if we take this h naught, if we look at the things on the left, this is a free particle state. So this h naught must be diagonalized by the free particle states. So this guy must be an eigenstate of h naught. So that's good. Also, we know that h here, this is the full Hamiltonian with the potential. So that means that the eigenstates of this guy, they're not the free particles, they're the full scattering solutions. So the eigenstates of H are these psi plus guys. And so that means we can start replacing things with the appropriate eigenvalues. For instance, we can take this H naught and act with it on the left, and that would pick up a factor of E k vector prime now, that energy. And now we can actually do something similar with this piece. And what we can do is we know that we can take the complex conjugate of this matrix element. So what we can do is say, well, if we look at, so we're going to look at this piece. Maybe I'll do it in blue or something. We can say, well, this piece, the k prime, now we have this E k prime minus h plus I epsilon inverse v psi k vector plus. We can write this as a complex conjugate of the complex conjugated matrix element. And how do you do a complex conjugation of the matrix element? Well, you would just flip the bra and the ket, and you would take the complex conjugate of the stuff in here. So this must be equal to psi plus k vector. Then it's e k vector k prime minus h, and now it's minus I epsilon. And v doesn't change, it's the real, it's just a potential. And here you would get k vector, and it's all that complex conjugated. It's a matrix element, so there's no, so you don't, it's not dagger or anything, it's just a number, so we can take its complex conjugate. And so now what we can do is we can recognize that this h now inside this complex conjugation can act on the left also. And now h is going to be diagonalized by that state. And so the eigenvalue is just going to be, again, the energy for k. So we can replace h with the energy at k. And then we would take the complex conjugate again. And so what do you get in the end? You'll get that this is equal to, I'm missing a -1 here. It's equal to the inverse of just these e to the k, ek factors. Again, now we take the complex conjugate, so this is plus I epsilon. And then we have k vector, and the only operator that's left over is the v. And so you're left with this. So that's nice, because now this matrix element is going to look an awful lot like this, and all that will happen is that we'll pull out these factors of E. So in the end, rewriting this again, so this is equal to, well, we can replace the inner product between the momentum states with the delta function. It's just the normalization for the pseudo eigenstates. And then we have 1 over ek vector minus ek prime plus I epsilon. That's from this first term. And then from the second term, we have a plus, same thing, except the e's are reversed. And then all of this is multiplying this matrix element, k prime v psi plus k. But I showed last time that this is equal to the matrix element of the T matrix. This is equal to k prime tk, where t gives the Born series. It's the potential, then, you know, the sort of, people call it sometimes the like a multiple scattering, but it's not really multiple scattering. It's you know, it's a little bit like multiple interference. There's still, the T matrix describes the scattering of a single particle off of a single target, and it's not like the particle scatters multiple times off the same target. It's not really like that. It's more like the interference between, there's more like an interference between the waves, the wave coming from different points in the target, and it's sort of there's no, I mean, it's sort of, it's just this, you know, it's just the iterative solution to the Schrodinger equation, but you can sort of interpret it as a kind of sort of like a multiple scattering approximation, but it's not really that. It's just a series in the potential. And so yeah, but sometimes it's called like a, people sort of misrepresent it as a multiple scattering kind of thing, but it's not. It's it's multiple scattering of the plane wave associated with the incoming particle, but it's not like the particle is actually scattering off of different targets multiple times or something. But in any case, so that was that Born series.
I have a question.
Yeah,
Can you go back up a little bit, please?
sure.
So when we're putting in substituting in the k plus 1 over such and such v times k in for the psi plus,
Mm-hmm.
why do we not replace the psi plus?
You mean here?
Yeah, when we go from there down to the next step, shouldn't the second term have a k at the
No, that's so no. This is yeah, not quite. So we're using we're using oh, you mean let's see. Oh, I see. Well, no, so sorry. We're doing that here. Oh, you mean when we replace psi plus? Why didn't we do it? Because we're doing a different equation. You see, this is not the same. There's two equations. There's this equation, and then there's also the Lippmann-Schwinger equation. That's why I put a little parentheses LS here, because we're not using this equation. We're using Lippmann-Schwinger. And Lippmann-Schwinger is first of all, it's the Green's function with just the kinetic energy.
Oh, it's the h, not the h. Okay, I see.
And it's just a recursive equation. It's just a rewritten Schrodinger equation. Oh, okay, so you can iterate this equation and get a series, the Born series. And then that Born series can be resummed up to get like the renormalized propagator, where h naught is replaced by the full h, which includes the scattering potential.
Okay, I understand.
So that's the Lippmann-Schwinger. This is a different equation. It's equivalent to the Lippmann-Schwinger, but I mean, it's subtle. This actually assumes more, right? It assumes that you can solve this Lippmann-Schwinger equation iteratively, and that you could resum that infinite series and write it as this propagator, but it's not clear. We do know how to solve for this propagator. Remember, we did that. That was that spherical wave propagator, the things we did right when we started this formal sort of stuff on scattering. We figured out what it is explicitly. But that's, just because we did that doesn't mean that we know how to do this operator, because that has a scattering potential in it. And actually, if the scattering potential has some properties like its long range, like if it doesn't decay fast enough, I think technically has to decay faster than 1 over r squared, then you can't invert that operator, and the Born series doesn't resum, so you can't. So this assumes a little more. But at any rate, we're assuming that we can do that and that the Born series can be resummed. And in that case, it's subtle. I mean, so that's just some of the issues involved. I think maybe that there's ways of thinking about it, even if the Born series isn't technically convergent. I'm not sure. It's sort of outside the scope of what we're going to do. We're just always going to assume that you can manipulate these objects without worrying too much about their whether or not this inverse exists. We're going to assume it exists, that you can find such an inverse. but it's subtle, and I think there are issues also when things are resonant. For instance, when you have a potential that has bound states, obviously something bad can happen if your energy here, right, is equal to the bound state energy, because then this will be zero. So you'll get, I don't know, you can get a blow up. You can get a blow up that's like different from the blow up that's corrected by this plus I epsilon. So I don't, there's issues with this for sure, that you can think about, but we'll just assume that those issues can be fixed. And if that inverse is sensible, then we can calculate. The rest of it just follows from applying the operator to its appropriate eigenstate and replacing the operator with its eigenvalue. So that's what we're doing. And then the thing that's left over is just this T matrix. And then we have to deal with this thing out front. But the thing out front is actually kind of interesting. It's remember, we always send the limit that epsilon goes to 0 in the end. Once you've cured all your divergences with the epsilon, you send the epsilon to 0. It goes away. So for the Green's function, it picks out the right sign for that spherical wave. But after you've done that, you send epsilon to 0 once you've used it to make sure that things don't blow up. And in this case, nothing is blowing up here per se unless this factor is equal to this factor. In fact, in the limit that epsilon goes to 0, you can show that 1 over x plus I epsilon plus 1 over minus x plus I epsilon, that's equal to minus 2 pi I times delta function of x. And as I emphasized in recitation yesterday, how would you prove something like that? All you need to show is that when x is not equal to 0, this thing vanishes. And it obviously does, because if x is not equal to 0, then you get, as epsilon goes to 0, you get a 1 over x minus 1 over x as 0. So that's good. And then the only other thing you have to show is that the integral of this thing is 1, right? Or 2 pi or whatever. Or, you have to show that the integral of whatever you're calling a delta function is in fact 1. And so you can actually integrate this thing. And show that it integrates to minus 2 pi I. And you would need to do that with contour integration. But so we don't do that. You'll be practicing similar things on the homework, so I sort of won't go into. Maybe you've seen this kind of thing before. Not sure, but yeah, that's what it is. So as you send epsilon to 0, this quantity just becomes a delta function in the energy, as it kind of must, because the S matrix, it's on shell. It conserves energy. And so what do we found? We found that well, I didn't actually. Let's go back. So what am I actually calculating? I'm calculating this inner product. So what we found is, so I'm getting ahead of myself a little bit. So what we found is that inner product the inner product between the inward scattering solution and the outward scattering solution, that's equal to this delta function. then it's equal to minus 2 pi I delta function in the energies. And then all that's multiplied by the T matrix elements. Well, this is great because, well, that's what we found the S matrix to be. This was the expression for the S matrix in terms of the T matrix in momentum space. So that's really nice because now you have even more connection between the S matrix and something kind of interesting, right? The inner product between the inward and outward scattering solutions to Schrodinger equation. And it's powerful because it lets you think about time reversal symmetry. And I sometimes talk about time reversal symmetry in the first semester, but I didn't this time. So time reversal is something, well, that literally reverses time. It's associated with an operator. And remember that things like rotations, right, and parity and so on, any kind of symmetry transformation like that, in quantum mechanics, it's associated normally with a unitary operator. But in the case of time reversal, the operator actually has to be anti-unitary. And an anti-unitary operator is a kind of funny operator. How it's defined is if you have any states in your Hilbert space like this, then if you take theta, this anti-unitary operator, and act with it on chi, and then you sandwich that with the operator acting on phi. Now, if this were a unitary operator, right, then I would normally go, well, this is nothing but, chi, and then must be theta dagger theta, phi, and that's equal to chi phi. That's if it were unitary, because I could then replace theta dagger theta with just the identity. But anti-unitary works backwards. It doesn't give you back just the inner product between chi and phi. It gives you the complex conjugate of that inner product. So you have to define it this way, and there's no sensible way. I can't define. I have to just tell you that this is the definition, because there's no way I can tell you that it's some kind of anti-identity, right, for theta dagger theta. So that's just how it's defined. We won't spend much time on it, obviously, because I didn't really cover it. But it's a time reversal operator. If you want to get into details, the reason for it is, remember that we have our canonical commutation relation between position and momentum. If you think about in your head what time reversal does, if you have a particle moving around or something, right? If you reverse time, right, take the movie of the particle moving around and you reverse it, you play it backwards in your head. What happens? Well, the particle moves right in the opposite direction of where it was going. So under time reversal, the momentum changes sign. P goes to minus P. If you're going to the left, then if you time reverse everything, then you go to the right. So if you're going this way, you apply theta to your particle, then the momentum will reverse. And because of that, because P goes to minus P and X stays the same, see, that's not good, because it means that under time reversal, this this commutation relation will pick up a minus sign. So it's not good. So you don't want to do that. You want the commutation relation between x and p to be the same under time reversal. So that's why it must be an anti-unitary operator. Because then because you have to take the complex conjugate after you apply, then that minus sign that you get from taking p to minus p is canceled because you have to take the complex conjugate of this guy. So you get back out the same sign again. But anyway, that's a little bit on the side. But what is the point for scattering? The point for scattering is that if you take the time reversal operator and apply it to one of these scattering solutions, then if you think about what that would do, what should that do? Well, if you have a scattering solution corresponding to an outgoing spherical wave, that's the plus sign, then if you time reverse, well, then the spherical wave should start going inward, right? And moreover, because we know the momentum changes direction, our vector k must go to minus k, right? Remember, this is labeling the incoming momentum. Well, if we time reverse everything, then if you send in a particle in, if you reverse time, then it must be going out back the way it came. So the solutions are connected. They're connected by time reversal. That's why this solution is interesting. We might have originally just thrown it out as unphysical, but actually it is interesting because it corresponds to a time reversed scattering solution. And of course, time reversal is kind of funny, playing movies backwards in time is sort of not intuitive because, things look weird. But anyway, it connects the two solutions that we found for the Schrodinger equation for scattering. Okay, but you can actually make use of this, right? Because now you can actually make a statement about the S matrix. Because if we do this is equal to psi k prime minus psi k plus. That's what we just derived, but I can now replace this, right, with the time reverse states. Well, this guy must be the same as theta acting on, well, okay, so two things. So first of all, the properties of the S matrix must be invariant under time reversal. So S matrix describes the scattering. It shouldn't. It should remain symmetric under time reversal. So that means that this inner product must be equal to what happens under time reversal. And because it's anti-unitary, the way we write this is we flip the order in which these guys are listed, and then we apply theta to both of them if this inner product is preserved under time reversal. And this is just a property of a sort of the anti-unitary. This is just using the property of theta, right? So this is, sorry. So forget what I said about the S matrix. All we need for now is just this property, right? We know that the inner product between two vectors, right, like this, like these guys, must be equal to the inner product where they're reversed and thetas are attached to them. So now I'm reversing these two guys, flipping them, and attaching little. Sorry. So I don't have to invoke any symmetry properties of S yet. Because what I said it's not quite right. So that's just using the anti-unitary property of theta. Okay. So then, uh, what we have here is now we can actually use the properties of the scattering states. So we're actually deriving a symmetry of S, essentially. So, okay, now we can use this property that we kind of intuitively know, that the time reversed outward scattering must be the same as the inward guy with an opposite direction for the incoming plane wave. And similarly, if we time reverse the incoming guy, then we should just get an outgoing guy with the flipped sign of the incoming momentum, like that. Okay, but this is just another matrix element for the S matrix. You see, it's the same as our original one. There's a minus sign here and a minus sign here, plus and plus. The only difference is that K prime is replaced with minus K, and K is replaced with minus K prime. So this is equal to minus K S minus K prime. So we've derived using time reversal a symmetry property of the S matrix. You see the matrix elements are related to each other like this. And of course, there must be an equivalent relationship for the T matrix because, well, you can see here, the T matrix is right over here. It has this, the matrix elements of S are just related to the matrix elements of T. So if the matrix elements of S satisfy this symmetry, the matrix elements of T satisfy that as well. So, and so that means that K prime T, K is equal to minus K T minus K prime. And this is called the reciprocity relation. It's a consequence of the properties of time reversal acting on the scattering states. It must be a symmetry obeyed by the S matrix, or equivalently the T matrix. So that's nice. We can do more. We can think about applying other kinds of symmetries to our S matrix and seeing what happens. For instance, we could apply rotational symmetry. If we apply rotational symmetry, what would that imply? Well, it would imply that if we take some unitary operator corresponding to some rotation R, if we simultaneously rotate the K vector, and we also rotate the K prime vector, both of them, then this doesn't change. If our scattering problem is spherically symmetric, then this doesn't change the matrix element, right? We can evaluate everything in a rotated frame of reference, so it doesn't. So the matrix element can't depend on the sort of orientation of K and K prime. We can, if we rotate both of them the same way, then those matrix elements have to be the same. So that means that the S matrix can only really depend on the relative orientation, right, between K and K prime. It can't depend on. It just matters, how you send in something and then where you're looking. Essentially, it's another way of saying it. And in that case, if you have that rotational symmetry, that means that these matrix elements we can write them as the following. We must be able to write them as a partial wave expansion that only depends on the relative orientation of k and k prime. So that means it can only depend on really the angle between k and k prime. So that means that this can be written as delta function k prime. Remember that the energies are, remember that these S matrix elements, they're all proportional to, they're on shell. So that means the energies are the same for k and k prime. Here, this first term's obviously they're the same because it's a delta function and k and k prime have to be equal. This term, you're forced to be the same. So the magnitudes of k, the k vectors have to be the same. So we know that the whole thing must be proportional to a delta function in the magnitudes of k and k prime. That's just energy conservation. And then what you're left with must be some kind of partial wave expansion of what? Of some kind of amplitudes that might depend on the magnitude of k times the Legendre polynomials of what? Well, the cosine of the angle between the two directions. So this must be k hat dotted with k hat prime. So if you have rotational symmetry, then the matrix elements of S in momentum must satisfy this property. Now, what else do we know? Remember that S is this unitary evolution operator. And we've yet to use that aspect of it. And the unitary evolution means that, if we take S and multiply it by S dagger, say, or, the reverse, what have you, it must give you the identity. Remember, because this is a unitary evolution. So if we just take the dagger and you multiply, that would be like scattering from, it basically just be the time reverse, right, of the unitary. I didn't erase it yet. I mean, that's what we started with. This is the definition of the S matrix. It's this guy. It's the interaction picture unitary evolution operator. So it's unitary. If you take S multiplied by S dagger, you should just get the identity. So we haven't used this yet. So let's see what the consequences of this thing is. Well, in momentum space, you can put in a completeness relation for the wave vector states, the momentum states. And what you would get is the following, right? That there must be a kind of relationship like this, that this is equal to a delta function between k and k prime. So this is just this is sandwiching this, the identity between k prime and k should give us a delta function, and then recognizing the identity can be written as S times S dagger, and then sticking in a completeness relation in terms of the free particle states in there. So we can actually evaluate this in using the partial waves, because we can now use sort of this expression for S, and we can calculate this integral, and we can look at what this unitary condition means for these F amplitudes. And the way you would do that is you would have to expand everything in sight in terms of partial waves. So, and that's going to be kind of tricky, because you'd have to take this matrix element and put this guy in here. You have to take this matrix element and put this guy in here with, the different Ks. And so you'll end up having to use some identities. For instance, you'll need to use the identity that the integral over orientations of the product of two of these Legendre polynomials, say k prime dotted with q, the one you're integrating, pl, q dotted with k hat, that's equal to 4 pi over 2l plus 1 pl k prime dot k. And it's actually, it's, if you put, you can even put different L's. So you'll have to have a separate sum for each matrix element you use here. And as it turns out, you have this nice orthogonality principle for the Legendre polynomials. You can use this formula to, kill one of the sums. So in the end, what you're left with, and then the other thing you need is, of course, the expansion of this delta function in partial waves. The delta function in partial waves is given by k squared delta k minus k prime. That's just kind of the measure part of the delta function. This is a 3D delta function. This is a 1D one. So there's, a factor of k squared that comes in. And the angular part of the delta function can be expanded in partial waves as follows. It's 4 pi over 2l plus 1. Oh, sorry, I have this a little bit backwards. Let's see. It's not, it's over k squared. And yeah, these are reversed, sorry. It's the other way. Yeah, we got this over k squared. This is 2l plus 1 over 4 pi. And this is pl k hat dot k hat prime. So this is like the radial piece is the delta function, and the rest of it is the angular delta function, which you can expand in Legendre polynomials like that. So, and then we can compare. We can look at both sides here. We can look at these, the expansion of this delta function. We can look at what happens when you stick in these terms in here and perform this integral using this. And in the end, you'll get an equation where you can compare sort of both sides. And what happens is this stuff will end up being equal to k squared delta k minus k prime. And then you'll have a sum over L. And you'll get you'll get 4 pi over 2L plus 1. You'll get a FLK squared. And you'll get the leftover, the Legendre polynomial, k hat dotted into k hat prime. So now you can compare these two things and just see what we get. Well, you'll see that this guy matches this guy, so that they kind of cancel out. These guys match that guy, so that's good. And so in the end, what we find is that the magnitude of this guy, it's constrained. It's like completely constrained by the unitary property of the S matrix. Like all this stuff here has to be equal to all this stuff here, right? So f of L times 4 pi k squared over 2l plus 1, all that has to be equal to 1 over k squared, 2l plus 1 over 4 pi. So, you know, it's like completely constrained. The magnitude of f of l is constrained to be 2l plus 1 over 4 pi k squared. That you can just work it out, take the square root. You see, this factor is just the inverse of this factor. So once you multiply it out, what you're left with is just this factor squared, and then you take the square root and you'll be left with this. But look how amazing that is. It means even though we started with this arbitrary factor, right? We said, well, look, rotational symmetry tells us that S must be equal to this, but we didn't say anything about these coefficients in here for the partial wave expansion. They could have been anything. But then what we recognize is if you know the S matrix is unitary, conserves probability, then actually the magnitude of this guy is perfectly constrained. And so if I drop the magnitude, if I just drop this and say, what does F equal to? Well, unsurprisingly, it must have this magnitude, and then the only other thing that it can depend on is a phase. So it can depend on a phase. And what's that phase? Well, it's, I can actually write it. It actually turns out to be 2I delta L. And these are the guys that I called the S matrix elements when we first started talking about scattering, right? In terms of the partial wave expansion. And you can actually show that that's what they are. In fact, you can go from the momentum space, you can go to angular momentum space representation. And what you would find is that if you calculate this, what you would find is that this is nothing but these E2I delta L, and then it's diagonal in this space. For, you know, spherically symmetric potentials. And you could do this by essentially starting with this expression, right, and sandwiching in some completeness relations in terms of the angular momentum states, or rather the reverse. You can start with this guy and put in some. Well, there's a variety of ways to do it, but all of them involve sticking in a completeness relation and then replacing the various matrix elements you get with either the appropriate wave functions or you know, what have you. So you can actually, you could stick in the completeness relation in K, for instance, in here. And then you would have to know what these kinds of matrix elements are. But you can calculate what that is, right? Because that's like, that's easy. To do this, what would you do to calculate this? Anyone have thoughts on how you calculate that? No takers?
Can't we use the same way, like completeness, by using complete?
Sure, you can use completeness, but for which version of completeness?
I'm not sure about that.
Well, yeah, that's right. You would use the position space one, right? So what's this equal to? Any takers for what that thing is? No takers. All right. Well, that's the spherical harmonic, right? Remember, first semester, the angular momentum states, their wave functions are the spherical harmonics. So this is the spherical harmonic, well, complex conjugated. How about this one? What's this one?
Is that like the radial function?
Nope. Any more takers? Oh, this guy. No takers. All right.
Momentum.
Sorry.
Momentum.
Yeah. But what is it? I mean, it's a function.
K over H bar. I'm sorry. P over H bar.
So these are, what is this? This is an inner product between a position and fixed momentum. These are the wave functions associated with a particle with a fixed momentum. So
With that
they're the
ECIKR, yeah.
yeah, they're the plane waves. So now you could, in principle, do this integral, and you'd have something. But then after you do that, you'd have to do the integral over k to like to get all this, and it'd be complicated. It would be tedious to do. You may or may not have to do it for homework. And in the end, you could show that these matrix elements and this angular momentum basis just give you these phases. So yeah, that's the idea. So everything is connected. The S matrix is the unitary evolution operator for scattering, and it connects the partial. You can write everything out in partial wave. It's what as I like to emphasize, the Hilbert space is always the same. It just depends on which representation you want to use, or you want to use position space, you want to use angular momentum. It doesn't matter. It's all the same stuff. It just depends on what kind of problem you have and what sort of basis is it easier to work in. Sometimes you want to look at the partial wave basis, that's the angular momentum basis. Sometimes you don't want to. Sometimes you want to keep things in momentum space, and then so yeah, it sort of depends on the problem. For instance, like the Born approximation, it's easier to formulate in momentum space, but you can of course you can expand everything in partial waves or convert everything to angular momentum space. You could also write the Born approximation in terms of the partial waves. It's also something you can do. You can convert between all these different pictures. And all these different approximations are related to each other. So hopefully that's the point of the section, is to show you that there's a general structure to scattering, and it's captured by the S matrix. Essentially, it connects all the different pieces of scattering together. It tells you, first of all, how the time evolution piece is related to the stationary solutions, which are these psi plus and psi minuses. It also tells you how that is related to the T matrix, and the T matrix is what you would use when you're doing the Born approximation, because the leading order, you can replace T with just the scattering potential. And then it also tells you how that's related to phase shifts, because we saw that the S matrix is really just those phase shifts, because in the end, you know, in the partial wave basis, S is really just equal to, it's diagonal in that basis, and it's equal to those phase shift things where I put it. These guys, e to 2I delta. So there's lots of possibility for like homework problems and so on, where you say, well, you know, what's the Born approximation in the partial wave for partial waves, or like, you know, like what's the phase shift equal to in the Born approximation? That's a typical question. You can also rewrite all the equations that we had in terms of different bases, right? So like we had this general equations here in terms of these kets, right? But there's nothing really preventing us from saying what's the Lippmann-Schwinger equation say in partial waves. You could do that too by just, you know, looking at the inner product of this with the angular momentum states, and then you would have some equation valid for each, you know, value of L. So you could sandwich this with LMs, right? And then see what you get there. So you can play games like this, sticking in completeness relations everywhere, and like replacing things with either spherical harmonics or plane waves. So there's a lot you can do, and you can, but hopefully you see that this formal structure in terms of the S matrix sort of connects all these things together into one thing, really. And it's not really that surprising, because all you're doing is just solving Schrodinger equation. So, all right, the last thing I want to talk about is what actually happens in scattering. You know, actually what happens is you would have to prepare a wave packet initially, and then it'll scatter against your target, and then it'll come out as a wave packet. And so the solution to this problem is, of course, time dependent, and the wave function for, say, the initial wave packet as it comes in, it has the following form, that there's a wave packet, which we can write in momentum space as some envelope times the plane wave. So that's what it is. And the stationary solution part is actually this guy right here. This is what the stationary part is. So in some sense, what we're doing when we're solving stationary, the stationary problem is just we're solving for that piece of the wave packet. And so initially it's this. Once it scatters, that part gets replaced by, you know, the scattered portion. But we can really, so we can understand this a bit more and see, you know, in more detail how the stationary solution is related to the wave packet thing. Typically for you know, you can set up your initial state however you want. So typically what's done is you have some uncertainty in the momentum of your initial particle. It's of course related to the uncertainty in the position. And you could describe the wave packet as, for instance, a Gaussian, properly normalized, sort of, there's a bunch of factors of 2 and pi and so on. But you can write it like this. If you have an uncertainty in position, that's related to the inverse of the uncertainty in the momentum. And then you can send in a particle with some initial momentum as right, and so the wave packet portion will look like this. So yeah, so you would, and of course, what is this? This is a Gaussian centered around some k naught, right? And so the idea is that if your wave packet is not very wide, if it remains, if it's not very wide in momentum space, which would mean that it has, it's actually, if the following condition is satisfied, that the uncertainty in position is much bigger in h bar t over m, then what we would have then is that you can use the stationary phase approximation to evaluate this integral for the wave function. If it doesn't spread, if the uncertainty in position is large, that means the uncertainty in momentum is narrow. And so most of the contribution to the integral will come from places where k is approximately equal to that initial momentum that you're putting in. Remember, you're integrating over all k here. And so you can use the stationary phase approximation where you assume that the main contribution of the integral is around k is equal to k naught. And so then you can start expanding things, and this is the usual kind of thing. We've done things like this before. And of course, omega is the frequency associated with the kinetic energy. So if I start expanding this, what can I do? Well, I'll leave this part alone for now, but I can start expanding the I omega t part. I omega t to leading order must be omega, and this is omega associated with the k. So to leading order, it must be the omega associated with k naught, right? It's the kinetic energy you put in. And then you have a Taylor series where you expand the omega in a Taylor series around k is equal to k naught. So you take its derivative with respect to k and evaluate it at k is equal to k naught. And then this would be the first term. And of course, this is a gradient. It's like a gradient in the k direction. And you would dot that into k naught, and this is times t. You get the higher order terms, but you drop those. So what does this become? This becomes ik dotted into r vector minus I d omega dk. Again, vector evaluated at k is equal to k naught. It's the gradient times t. And we're left with a minus I omega k naught vector t. It's this term. And then we're left with this other k naught piece, which is plus I d omega k dk. Evaluated at k is equal to k naught times dotted into k naught t. And again, omega here is just h bar squared magnitude of k squared over 2m. So it's easy enough to take its derivative. And you see that what you get is that when you take its derivative, this actually becomes twice this guy. Because if you take a derivative with respect to k, you'll get basically a 2k, and then you multiply by k again times t. So you end up, these two terms just combine and give you a plus I omega associated with the k naught times t. Because this term is just twice this guy without the minus sign. Because you can just take the derivative of this. And so in the end, you see that that stuff in the exponential is nothing but e to the I k dotted into r shifted by a velocity, v naught t. And then there's also a phase. plus I omega k naught t. So that's what this guy is. So that's our final result here. So the stationary phase approximation just tells you that your wave function for the time-dependent problem, what does it look like? It looks like a phase and times the wave function of your initial state just shifted by some amount v naught t, and this is the velocity, like that. Because if you take this and you just place it back into here, then there's no longer, we can just do the integration over k, and it'll be the same as the integration as if there's no, as if you just evaluated at t equals 0, because this omega no longer depends on k, right? We've Taylor expanded it. And the first term in the Taylor series just gives you a shift in the position of the thing. So this just describes a wave packet that's being translated along with the velocity v naught, where v naught is just h bar k naught over m. Just the initial velocity from the initial momentum you put in. So that's the initial wave packet that comes in, provided that it's narrow enough in momentum space, so it'll just get translated along. And to get the scattered part, well, all we would do is, and this is where I'll leave off for now. I guess I'll still need a little bit more time. But what you do for now is you remember that, so the full solution must be the, what we just calculated, the sort of incoming part, plus whatever the scattered solution is, which also depends on time. And this guy, what is this guy equal to? Well, it's going to be just the same kind of expression where we integrate over the wave vectors, and it's going to be some, again, the same envelope function, but now it's the scattered portion of our stationary solution. Remember I said that this part of the solution is the stationary solution part. So you just replace this with the scattered portion. And the scattered portion is, of course, our friend, the scattering amplitude, which depends on k prime and k. This is k prime. And we have, it's multiplied by the outgoing spherical wave. And then you're left with the e to the minus I omega kt. And now you could do the same thing, do the stationary phase approximation. And I guess that's what we'll do next time. And we'll just show that under the stationary phase approximation, that this integral over k just goes away. And so all you're left with is just the envelope piece, which just gets translated around in time, and then it's multiplied by the stationary solution, which we already know how to calculate because that's what we've been doing this whole time, is just calculating the stationary part.